Hello, and welcome back to our continuing discussion on thermodynamics. In an earlier lecture, we looked at the effect of heat on a substance and how it could change the temperature of that substance. But I'm sure it is within your experience that when you add heat to something, you might also change its phase. For instance, water ice might melt into liquid water, or liquid water might boil into steam, or the reverse of those processes, steam back to liquid water freezing into ice. These, of course, are called phase changes. And on the screen, we see the names of the different phase changes that we would normally encounter. We're sticking to the standard phases of matter. We're not doing anything exotic like plasmas or superfluids. We're just sticking to solids and liquids and gases. And if you have a solid going to a liquid, that is melting. If you have a liquid going to a solid, that is freezing or fusion. A liquid going to gas is boiling or vaporization, whereas a gas changing phase to a liquid is known as condensation. Less commonly occurring, but still possible, we have the situation of a solid going directly to a gas, and that process is called sublimation, or a gas going directly into solid form, and that's called deposition. Although we don't normally encounter this, one phenomenon with which you might be familiar is dry ice. Dry ice is actually frozen carbon dioxide, and at ordinary pressure, the solid carbon dioxide will sublimate directly to a gas. So there's no liquid transition, and that's why it's called dry ice. If we need to determine the heat involved in causing a change in phase, we can make an assumption that is really an extremely good approximation for the measured values that we get in experiments. This assumption is that when a substance is changing phase, it is not changing temperature. And for that matter, when a substance is changing temperature, it is not changing phase. So it's either one change or another. Either when you add or remove heat, you're changing the temperature of a substance, or when you add or remove heat, you're in the process of changing the phase of a substance, but you're never doing both simultaneously. Let's take a look at water as an example. You probably are aware of the fact that at standard pressure, water melts, ice melts at a temperature of 0 degrees Celsius, or water freezes at a temperature of 0 degrees Celsius. But while it is doing the melting or the freezing, it is at 0 degrees Celsius. It's not like it makes an instantaneous transition from -1 degree Celsius to +1 degree Celsius. You start with ice at 0 degrees Celsius, and the first thing that happens is you get water at 0 degrees Celsius. Or you start at water 0 degrees Celsius, you freeze it, and you get ice at 0 degrees Celsius. Once the phase change is entirely completed, then you can start looking at changing the temperature. If we want to calculate how much heat is necessary to invoke a change in phase, there are three things we need to know. We need to know the mass, the amount of substance. We need to know what the substance is. And then we need to know what phase change is occurring, because the amount of heat necessary to melt is given amount of a substance is not the same as the amount of heat necessary to boil that same amount of substance into a gas. We don't need to know the temperature just to calculate the energy of a phase change. We'll see how it does show up later, but just for that particular phase change, the formula does not require temperature. What it does require is a material-dependent property called the latent heat. The latent heat, we do not have a theoretical formula for it. It is an empirically determined quantity. In other words, we experimentally measure it. And we have to worry about the substance and the phase that is changing. For instance, we can take a look at water. Water has a latent heat for melting, positive 333.7 joules per gram. So in other words, if I have a gram of ice and I want to melt it into a gram of water, I need 333.7 joules. On the other hand, that same gram of water, if it's at the boiling point, if I want it to go from entirely liquid water to entirely steam, that same gram of water requires almost 10 times as much energy, 2,256 joules. If we are talking about the reverse processes, the number is the same, but we stick a minus sign in front of it. If I have 1 gram of water at 0 degrees Celsius and I want to turn it into 1 gram of ice at 0 degrees Celsius, I have to remove 333.7 joules. So I would say that the latent heat of fusion, or freezing, is negative 333.7 joules per gram. And if I have 1 gram of steam and I want to condense into 1 gram of water, I'll have steam at 100 degrees Celsius converting into water at 100 degrees Celsius. I have to remove 2,256 joules per gram. So the latent heat of condensation for water is negative 2,256 joules per gram. The latent heat of vaporization / condensation is about 10 times larger than the latent heat of melting / fusion, as I pointed out earlier. Why is that? And part of the answer comes from the fact that when we are going from a solid to a liquid or back again, the volume of the sample isn't changing by very much, which means that the separation between the atoms or the molecules making up the substance doesn't change by a whole lot. However, when we go from liquid to gas, we are requiring not only, we're requiring that these atoms and molecules spread out and they separate from each other. Now, in solid and liquid form, there's actually some attraction between the atoms or molecules in a substance. That same is true in gas, but we need to overcome that attraction to get it from the relatively dense liquid phase to the relatively rarefied gaseous phase. We have to get these atoms and molecules separated from each other. So this attraction that exists between them that keeps them close together in solid or liquid form, we have to break apart that attraction. So it requires a lot more energy. We have to do a lot more work to pull them apart, and that work manifests itself as a larger latent heat of vaporization. Okay, let's combine all of this stuff together. By all of this stuff, I mean, let's consider what happens when we heat up a sample, and not only do we change the temperature, but we change the phase. We could, in principle, start off with a sample that is in solid form and below the melting point, the freezing point. So we start off, say, with ice at negative 20 degrees Celsius. We then add heat to it, and we increase the temperature of the ice until we get to the melting point. We use MC delta T for that. We then have to actually melt it, and that's where we have the latent heat. And the formula for the heat involved in a phase transition is M times L. So you'll see M times L subscript N added on to the first term. Then we could imagine taking this now water at 0 degrees Celsius and raising it all the way up to becoming water at 100 degrees Celsius. We had to have to do MC delta T. Then we would have to change the phase of that water. We'd have to go from water to gas. Being a phase change, we have to use the formula ML. And then finally, we take that gas to whatever desired final temperature we wish. And for that, we would have MC delta T. Now, if you look at this formula near the bottom of the slide, you'll see that my latent heat quantities have different subscripts. L subscript M for melting, L subscript V for vaporization. But we also have subscript S for the specific heat and the delta T. The specific heat for a substance in solid form isn't necessarily the same as the specific heat of the substance in liquid form, and that in turn is not necessarily the same as the specific heat of the substance in gaseous form. And then, of course, delta T, it depends upon where we actually start. The delta TS is the initial temperature of the solid to the melting point. The delta TL that we see in this full-length formula is from the melting point to the boiling point. And then the delta T that we see for the gaseous part is from the boiling point to whatever desired final temperature. Now, we could do also just a subset of these quantities. This is as bad as it gets. But suppose we start off with ice at -10 degrees Celsius and we want water at 30 degrees Celsius. Well, we'd still have the MC delta T for the solid to get it from -10 degrees to 0 degrees. We'd have to do the phase change for solid to liquid, so we have M times L for that. We now have water at 0 degrees. And then we would need water at 0 degrees to the final temperature of 30 degrees. We're not bringing it up to the boiling point, so we don't need the MLV. And certainly, since we aren't entering the gaseous phase, we don't need the MC delta T for gas. So you have to analyze the problem. The expression you see on this slide is as bad as it gets. You need to determine which parts you need in a given problem. Let's take a look at this example. We have 51.5 grams of silver that is initially at a temperature of 25 degrees Celsius. And all we want to do is boil it off into its gaseous phase. How much heat is required? Well, what information do we need? We are starting with solid silver. We need to raise the solid silver to the melting point. We then have liquid silver. We then need to raise this liquid silver to the boiling point, and then we need to boil it. We don't need to raise the temperature of the subsequent gaseous silver. We're just asked, boil it off into silver vapor. So we need information about silver in its solid phase. We need to know, for instance, the specific heat of silver as a solid, and we also need to know the melting point of silver. Then we have silver in the liquid phase. We need to know the specific heat of silver in the liquid phase, and we need to know the boiling point of silver. Along with those, we need the latent heat of melting for silver, and we need the latent heat of vaporization for silver. Fortunately, these things can be found in appropriate locations. The specific heat of silver in solid form is 0.240 joules per gram times degree Celsius. The specific heat of silver in liquid form is just a little bit larger, 0.310 joules per gram times degree Celsius. The latent heat of melting for silver is 104.2 joules per gram. The latent heat of vaporization of silver is 2,630 joules per gram. We need the melting point, that's 962 degrees Celsius. We need the boiling point, 2,163 degrees Celsius. So if you look at the little graphic there, we start with solid silver at 25 degrees Celsius. We add heat until we get solid silver at 962 degrees Celsius. We then add heat until we get liquid silver at 962 degrees Celsius. We keep adding heat until we have liquid silver at 2,163 degrees Celsius. And then finally, we add heat so that we can boil it into gaseous silver at 2,163 degrees Celsius. And that would answer the question being asked, how much heat is required to boil it off into silver vapor. So we we need MC delta T for the solid, we need ML for the melting, we need MC delta T for the liquid, we need ML for the boiling, and we're done. The total heat necessary is 1.716 times 10 to the 5 joules, 171,600 joules. Let's look at something a bit more complicated. We have 15.9 grams of ice at negative 18 degrees Celsius, and we drop it into liquid water at 36.2 grams of liquid water starting at 3.5 degrees Celsius. What happens? What happens when all of this ice and water reaches thermal equilibrium? What is that final situation going to be if we assume no heat enters or leaves this system? We need to look up some properties of water. The specific heat of water in solid form is 2.1 joules per grams times degrees Celsius. And the specific heat of water in liquid form is 4.186 joules per grams times degrees Celsius. We're dealing with either solid water or liquid water, so we only need to worry about the latent heat of melting or freezing. The latent heat of melting, as we saw earlier, is 333.7 joules per gram. Now, at this point in time, we need to make a guess. What is the final state of the system going to be? Here are the possibilities. We have a final state in which everything is frozen as ice, probably greater, definitely greater than negative 18 degrees Celsius and probably less than 0 degrees Celsius. That's one possibility. Another possibility might be that all of the ice melts into liquid water, and what we would have is a solution or a substance that is entirely liquid water somewhere between 0 degrees and 3.5 degrees Celsius, or we have a certain amount of ice and water, so it's just like a glass of ice water, at 0 degrees Celsius. Some of it is in ice form, some of it is in water form. It's kind of stuck in that transition because there isn't enough heat to fully accomplish the melting or the freezing. Let's take a look at these possibilities. Now, the heat necessary in the water is going to be the mass of the water times the specific heat of the water times the change in temperature of the water. And the heat for the ice, if we assume that everything winds up at a temperature greater than 0, is mass of the ice times the specific heat of the ice times the change in temperature for the ice going from its initial temperature to the freezing point. Then, if we're assuming that everything is liquid water, this ice has to melt. The 15.9 grams of ice has to melt, so we need ml. And then, this now melted ice, which is now water, has to go from 0 degrees to whatever the final temperature is going to be. Now, this is an assumption. I don't know if this is correct. We need to see if we get an answer that makes sense. And we need to determine the final temperature. If the setup makes sense, and if we assume that no heat is entering or leaving the system, so that Q system is 0, if we go through all of the math and solve for the final temperature, we wind up getting a final temperature of negative 24.7 degrees Celsius. And that doesn't fit with our assumption that if we wind up with entirely liquid water, that it would be between 0 and 3.5 degrees Celsius. This answer doesn't make sense. It has to be wrong. Let's move on to a different guess. Maybe our guess is that all of this winds up at 0 degrees Celsius with some amount as ice and some amount as water. So perhaps the water is brought down to 0 degrees Celsius, and perhaps some of the ice melts. Let's look at the numbers. So again, the heat for the system is 0. Now, if all of the ice is brought down to if all of the water is brought down to the freezing point of ice, we have 36.2 grams of water. It's changing temperature, so the specific heat in liquid form is 4.186. The final temperature is 0 and the initial temperature is 3.5. If we have the ice brought up to 0 degrees Celsius, its heat is 15.9 grams of ice times 2.1 for the specific heat. It's brought up to 0 degrees, so delta T is 0 minus negative 18. Let's assume some of the ice melts. How much of that ice melts? Well, that's what we'll find. But we have to multiply it by the latent heat of 333.7. And we go through the numbers, and we find that the amount of ice that would have to melt is negative. That's a nonsense answer. Our guess is wrong. What about the other option? The material, the substance at the end in thermal equilibrium, none of the original ice melts, but it is brought up to 0 degrees Celsius. On the other hand, the water is brought down to 0 degrees Celsius, and some of it freezes. Again, the heat for the system is 0. We have the 36.2 grams of water brought down to 0 degrees Celsius, and some of it freezes. And notice that I'm using the latent heat of negative 333.7 because the latent heat of freezing is the negative of the latent heat of melting. We also have the 15.9 grams of ice going from negative 18 degrees to 0 degrees. And if we plug in all of this, we get that the amount of material that was originally liquid water that freezes is 0.2 grams, which is reasonable. This is something that makes sense. So what we wind up with in the final state, the 15.9 grams that was originally ice doesn't melt. It's just now at 0 degrees Celsius. The 36.2 grams of water some of it's going to freeze. And the liquid that is still remaining is going to be at 0 degrees Celsius. Since 0.2 grams of the liquid water freezes, we lose 0.2 grams of liquid, we gain 0.2 grams of ice. We now have 16.1 grams of ice and 36 grams of water, all at 0 degrees Celsius. So this is a bit painful, but if you understand the rationale and the guesses that are being made, that would put you in good stead. Is it possible for water ice to sublimate directly to steam? Now, if you've ever pulled ice out of the freezer, you might see some vapors above it, but that's really more the condensation of water vapor in the air. It's not ice sublimating directly to steam. But under the right conditions, you can take water ice and have it turn into directly steam. But what are the conditions? It certainly doesn't happen in regular atmospheric conditions. To understand the behavior of a substance and its phase changes in situations where the pressure can be wildly different, where the temperature can be wildly different than what we're used to, we have something called a phase diagram. A phase diagram has pressure on the vertical axis and temperature on the horizontal axis, and then it can be a rather confusing set of curves. Let's take a look at an approximation of the phase diagram for water. On the horizontal axis, you see temperature. On the vertical axis, you see pressure in atmospheres. The vertical demarcation 1.0 represents 1 atmosphere. This is what you are used to. And the slight problem here, that's what it should be. The lines that we see represent boundaries. At 1 atmosphere, if you look on this horizontal line, if we move left to right across this horizontal line, we move through increasing temperature. And we see the solid region, and at about T equals 0 degrees Celsius, we go from solid to liquid. And as we continue along this horizontal line at 1 atmosphere to the right, it again crosses another curve, and it represents a boundary between liquid and gas. The point at which it crosses from liquid to gas would correspond to a temperature of 100 degrees Celsius, the boiling point of water. So there is some ordinary behavior represented there, but we also see behaviors for situations other than 1 atmosphere. If we bring the pressure low enough, if the pressure is below 0.006 atmospheres, if I'm at, say, a pressure of 0.003 atmospheres, and I start increasing the temperature, what I run into is a boundary between the solid region and the gaseous region. When the temperature is very low, when the pressure is very low, it is possible for water ice to directly sublimate to water gas, aka steam. And we also see that steam doesn't have to exist at 100 degrees Celsius or higher. If the pressure is noticeably less, we can get steam at much lower temperatures. And if the pressure is really low, we can have steam even at below 0 degrees Celsius. This obviously is not something we encounter naturally in atmospheric conditions, but when you start looking in deep space where the pressure is very low, where the temperature can be very low, these sort of situations are much more common. There are also some other rather surprising things. Where these boundaries meet, where the boundary between solid and liquid, the boundary between liquid and gas, and where the boundary between solid and liquid meet, this is called the triple point. And if you can get water at exactly this triple point, where the temperature is 0.01 degrees Celsius, where the atmospheric pressure is 0.006 atmospheres, then the water kind of exists in all 3 phases at the same time. It is just equally intermingling, becoming a gas or a liquid or a solid. It's a random process. There are videos of water at this triple point. And you see steam, you see liquid, you see solid just randomly popping into existence from one phase to another phase, and then just randomly transforming into one of the other phases. There's also a situation of a critical point. At the critical point, if we are at a sufficiently high temperature and a sufficiently high pressure, the material is kind of amorphous. It's not just liquid, it's not just solid, it's not just gas, it's a mix, and that's a rather unusual circumstance, obviously. What happens at more extreme pressures and extreme temperatures? And here's a more sophisticated phase diagram for water. You can see how the boundaries between liquid and vapor, solid and liquid, and solid and gas are similar to what we saw before. Note that the vertical scale is a logarithmic scale, so it's a bit crazy in that regard. And that the temperature scale is in kelvins. But we see other lines right there, and we see all these Roman numerals. It turns out that water ice comes in many different formats. Water is a crystalline solid, but the shape of the crystals at the molecular level can vary wildly. And we find water ice with different properties. Again, these are things that we don't encounter on the Earth. We see water 1 on the Earth, regular old, the ice that you get out of your freezer, the snow that falls from the sky, that's ice 1. But under more extreme circumstances, again, like in outer space or in the interior of planets, where you can have lots of pressure and high temperature, you can get solid water that has decidedly different properties. For instance, ice 11xi, which is water ice that is extremely cold, less than 100 degrees Celsius. That water ice is extremely brittle. If you take a chunk of regular ice and drop it onto the ground, it'll splinter and maybe a couple of pieces might fall off here and there. But if you take this brittle water ice 11 and drop it on the ground, it's more likely to just shatter into a million little pieces. So this is some sophisticated stuff. I'm not going to run any calculations. We're going to stick with ordinary ice, ordinary water, ordinary steam when we have calculations. But I want you to be aware of the existence of other types of ice. Water ice is actually a very complex thing to study. And we're not even sure that we know up to 18 different forms of water ice, and there are predictions of several more possibilities under even more exotic circumstances. It's really some pretty fascinating stuff. I also want to show a phase diagram for carbon dioxide. Again, you see the vertical axis is logarithmic, but we do see one atmosphere highlighted pretty clearly. And as we move from left to right across it, you can see that we go from a boundary from solid to gas. And this boundary is at about negative 80 degrees Celsius. So dry ice is extremely cold. Negative 80 degrees Celsius or colder at one atmosphere. But then when it changes phase at one atmosphere, it doesn't melt. It just goes directly to carbon dioxide gas. But it is possible for there to be liquid carbon dioxide, and carbon dioxide also has a critical point. So to understand the triple point where it's solid, liquid, gas simultaneously, I like to think that ketchup is at least near the boundary between solid and liquid, because you probably run into the phenomenon that ketchup is pretty hard to get out of a bottle. But if you shake the bottle enough, you might get it to a point where it reaches that boundary between solid and liquid. And it's not exactly melting, but it does start to flow a little more easily. It becomes a little bit less solid-like and a little bit more liquid-like. Another related topic to phase change is the idea of evaporation. If you have a glass of water and you leave it on the countertop overnight, when you get there in the morning, the level of water is going to be less. Obviously, we know this as the phenomenon of evaporation, but why is water changing to vapor when we're not intentionally boiling it? And the answer is in this curve right here. This curve is called the Maxwell-Boltzmann distribution. What does it represent? If you look on the vertical axis, you see it labeled number of particles, and if you look on the horizontal axis, you'll see it labeled speed. Now, we looked at the average speed of a gas particle in an ideal gas. 3/2 kb T is equal to 1/2 mv squared on average. But that's the average value. Individual particles can have a value that is different from the average value. And the distribution of speeds is called the Maxwell-Boltzmann distribution. You'll see that virtually no particles have a speed of 0. But as we examine higher and higher speeds, we see more and more particles at those speeds. We'll find a speed at which we have the maximum number of particles. But then as we go above that speed, the number of particles at higher and higher speeds gets smaller and smaller. But there are going to be some particles that have exceptionally high speeds, just random luck. and they'll have speeds high enough that they feel like they're boiling, that they're moving around so rapidly, just like they would if we were trying to boil liquid water at 100 degrees Celsius. A small number of those particles are moving fast enough, just like they were boiling. And so they do boil off. They do vaporize into steam. Now, yes, the energy remaining behind in the water is less, but there's still going to be all of these random collisions between the water molecules, and just through random luck, some additional ones will still develop enough speed to feel like that they're at the boiling point. And so over time, you're losing internal energy in the liquid, but there are still just random collisions for individual particles that cause them to vaporize, and over time, the amount of water in the glass will diminish. This gives rise to the idea of vapor pressure. Vapor pressure is basically the amount of vapor above a liquid that is just the result of these particles in the liquid having enough energy to effectively boil off into a vapor format. That's enough for now. Take care. Bye-bye.